Now, rocket firing is an awesome demonstration of tremendous power. I think we should find out how it works. One of the best authorities on this subject is the rocket historian, Willie Ley. Here, Mr. Ley explains the operation of a rocket motor to some of the artists working on the picture.
This is an actual propulsion unit from a V2. And this strange-looking device is both the heart and muscle of a rocket, its motor. Now, all earthbound engines have to burn oxygen from the surrounding atmosphere. But the high-altitude rocket motor has to work in outer space where there is no oxygen. To overcome this, we carry a tank of liquid oxygen here. When burned with a fuel, in this case alcohol, it produces an intensely hot, torch-like flame that would quickly melt the motor. However, we cool the motor by first circulating the alcohol fuel around it, until this fuel finally reaches the point where it is sprayed, along with the oxygen, into the combustion chamber. When this steady flow of alcohol and oxygen is ignited, it produces a continuous explosion which blasts the rocket away in the opposite direction. Here again we have action and reaction. If this motor is placed in a streamlined hull with suitable controls, it can reach a high altitude in a very short time. The V2 rocket motor only operates 65 seconds to a height of 20 miles. But then the V2 has gathered so much speed that it will coast upward to an altitude of 114 miles before gravity begins to pull it back to Earth. Notice that the rocket does not nose over in the thin upper air, but it falls tail first until it re-enters the denser atmosphere where the air, acting on the tail fins, turns the rocket nose down. Early in 1949, space history was made when the payload in the nose of a V2 was a small rocket called the Walt Corporal. When the large V2 reached its maximum speed, the smaller rocket was ignited. This additional boost in speed enabled the Walt Corporal to set a new high-altitude record of 250 miles. This day marked the first time that a man-made object reached outer space. This was accomplished by using a double rocket, then secretly known as Project Bomber. However, we refer to it as a two-step or two-stage rocket.
Is it possible to build a three-stage rocket?
Yes, as a matter of fact, that's the next logical step. Here's a rocket I have designed that has 3 stages. It would stand about 70 feet high or a little taller than the old V2. Here you can see the 3 sections, each one having its own rocket motor. If somebody will please make a sketch for me, perhaps I can explain how it will work. Good. Here we show our rocket in its launching position. The first great blast starts to lift it, and after gaining initial speed, the first section is cast off at 20 miles up. At 45 miles, the second stage is released. The third stage now fires until it reaches an altitude of 70 miles. At this point, our rocket has now attained a tremendous speed and the motor shuts off. Its forward momentum would carry it straight out into space if it were not for the Earth's gravity. This downward pull of gravity bends the upward course of the rocket into a curved path. And if the rocket's speed going away from the Earth creates enough centrifugal force to balance this pull of gravity, our rocket will continue coasting in its curved path around the Earth indefinitely.
Mr. Ley, is there another way we can illustrate this?
Yes, let's explain it this way. If the rocket were to move at a slower speed, the pull of gravity would soon overcome the rocket's momentum and it would return to Earth here. If we add a little more speed, the path of the rocket becomes longer. And it goes farther before it returns to Earth here. So if we have our rocket go fast enough, it will eventually follow a curve which matches the curvature of the Earth and will not fall back. We might say that the rocket falls around the Earth as long as it maintains sufficient speed.
But how does it maintain this speed with the motor shut off?
Remember, our rocket is traveling above the atmosphere in space, where there is no air friction to slow it down.
How fast does it have to go to stay up there?
Now that depends on how high we want the rocket to be as it circles the Earth. Let's use the altitude of 1,075 miles. Because at this height, the rocket will have to go nearly 16,000 miles per hour and will make a complete trip around the world every 2 hours. A few adjustments in its course will be necessary, but this can be accomplished from the ground by remote control, after which the rocket will continue to coast freely in space forever.
In other words, the rocket will stay up there just like the moon.
Yes, it will circle the globe as a man-made satellite.
What is the purpose of having this satellite up there?
Having this instrument-carrying rocket moving around the Earth will give us a lot of important information which we'll need before we dare let a man make his first trip into space. To run the scientific apparatus contained in the satellite, a mirror will focus the intense rays of the sun onto a silicon battery, converting solar energy into electricity. There will be a television camera to give pictures of the Earth as it appears from 1,075 miles up. We will collect very important data on the effects of the mysterious cosmic rays. Even hits by meteorites the size of a grain of sand will be recorded. Every 2 hours, when the rocket moves over the North Pole, its radio will transmit a stream of data to a receiving station below. This will be the first outpost in man's conquest of space.
One of the big question marks of future space travel will be man himself. How he will react mentally and physically to this unearthly experience is the concern of a new field of science called space medicine. Helping us illustrate this interesting problem is the scientist most noted for his pioneering work in space medicine, Dr. Heinz Haber.
When man steps into his rocket ship and leaves the Earth behind, he must be well equipped to survive in the hostile realm of outer space. To portray the complex problems of space medicine, we have designed a sort of common man. A man just like you and me. We will find out what will happen to him on a trip into space. In a way, he's going to be our space guinea pig. That makes him a brand new biological species. I think we should call him Homo sapiens extraterrestrialis, or spaceman. Since he was picked at random, we cannot tell whether he will be able to tolerate the tremendous stresses to be placed upon him when the rocket ship is fired into space. He gets an inkling of these stresses when he rides in an automobile. When he steps on the accelerator, the car moves forward and he is gently pressed against the back of the seat. His body resists any change of motion. When he comes to a stop, his body tends to move forward. On a test rocket sled, which is pushed forward at tremendous accelerations, the force of inertia is much stronger. We are all familiar with centrifugal force. We duplicate this force in the laboratory by using human centrifuges. These machines artificially create on man the crushing pressure he will have to endure in a rocket takeoff from Earth. His body weight increases until he blacks out and finally loses consciousness. From tests like these, we have learned that man will have to assume a reclining position when his rocket takes off into space. In this attitude, the stresses will be more evenly distributed along his body. He will then be able to tolerate pressures of up to 9 times his weight or more, as it occurs in a rising rocket. When the rocket engine finally stops, man will face his next big problem, weightlessness. Without support, he will be floating freely, drifting, tumbling, and twisting helplessly. In space, a man, a feather, a bubble, or a piece of iron will have the same weight, or rather, no weight at all. However, man is designed to live with gravity, the down-pulling force which Sir Isaac Newton first explained.
Any two bodies attract each other with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. Or, what goes up must come down.